Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about the limit comparison test. Very much related to the direct comparison test, very similar concept. Okay, but again, we'll be able to quickly see the need for it, what you would need it for, that you wouldn't, be able to use the direct comparison test for. Okay, so let's get started on this next test. Okay, so first question. Let's use the direct comparison test from the previous video to determine if this series converges or diverges. Well, this is 1 over n squared minus 1. All right, so that's pretty easy to figure out. We're going to compare that to 1 over n squared, right? It's almost the same thing. This is a convergent p series. P is greater than 1. So now we're going to take 1 over n squared plus 1, compare it to 1 over n squared. And again, we know this series converges. So let's take a look at our inequality sign. Our inequality sign goes this way. So 1 over n squared plus 1 is greater than 1 over n squared, right? The denominator is smaller than this one, which means a bigger result. Or you can multiply both sides by the denominators and see it pretty easily that the one is bigger than the other. Okay, now, but there's a problem with this. I know that the series that's smaller converges. So again, if we go back to our little pictures that we had before, here's my series that converges. But then I have another series, 1 over n squared minus 1, that's larger than 1 over n squared, right? I know this one converges. The question is, what does this series do? Well, the direct comparison test, I don't know what this other series does, because this series, it's bigger than this one. So it might come down and converge, but there's nothing pushing it down. I mean, it can go straight up to infinity if it wants. So I don't know. So the direct comparison test here, it fails. It doesn't work, right? I can't use the inequality in this direction. So then what am I to do now? Because I have a series certainly to compare it to. It's pretty easy to find it. But I can't use that direct comparison test. That's where your limit comparison test comes in. So let's take a look. The limit comparison test says, suppose that you have two series, a sub n and b sub n, both greater than 0. If the limit as n approaches infinity of a sub n over b sub n is equal to L, and L is a positive finite value, then either both series converge or both series diverge. So here's how this is going to work, okay? Basically what we're going to do is it's similar to the direct comparison test. We're going to pick a series called b sub n to compare our original series to. Like, for example, in the last slide, it would have been 1 over n squared. I know this is a convergent p series. P is greater than 1. Okay? Again, I'm comparing it to the last slide, 1 over n squared minus 1. And then I'm going to take the limit as n approaches infinity of, here's my a sub n, here's my b sub n. 1 over n squared minus 1 over 1 over n squared. And I want to find its limit. So I can swap this around here, right? It would give me n squared over n squared minus 1. Divide everybody by the dominant power, or you can use L'Hopital's rule, right? So divide everybody by n squared, I suppose. That's going to give me 1 over 1 minus 1 over infinity. That goes to 0, 1. So the limit, when I divide them, is 1. That's a positive and finite value. So now my conclusion is either both series converge or they both diverge. Well, the series I compared this to originally converged, right? It was a convergent p series, p greater than 1. So then I know that 1 over n squared minus 1 converges by the limit comparison test. Okay? So I'm sure that this series then converges by the limit comparison test. That's how this test works. So again, it's similar to the direct comparison test in that the first thing we do is say, okay, let's find another series that we actually know whether it converges or diverges, work with that first, and then go from there. All right? Okay. Oh, well, we just did 1 over n squared minus 1. So let's go right through this slide. We just did it on the previous slide. All right, let's try this one. This is a little more complicated. It's the sum from n equals 1 to infinity, n minus 1 times n squared plus 1 over n plus 2 times n to the fourth plus 2 quantity squared. Okay, so again, we need to find a series that we can compare this thing to that we know whether it converges or diverges, right? So the question is, how would we do that? Well, what we need to do is, if we were to multiply this out, we need to find what power dominates in the numerator, what power ultimately controls the numerator terms, and what power ultimately controls the denominator terms. And we're going to divide them and make a series out of it. So for example, if I were to multiply this out, the largest variable exponent would be n cubed, right? So we're going to put n cubed up there in the numerator. In the denominator, well, I'd have to multiply n plus n to the fourth, right? So this would be n to the fourth times n to the fourth. That would be n to the 8. And then another one would make n to the 9. I get a bunch of other powers as well, but they don't matter. Okay? So that would give me n to the third over n to the 9, which is 1 over n to the 6th. So the question is, what do I know about 1 over n to the 6th? This is a convergent p-series. P is greater than 1. So now, what I want to do is I want to compare these two. I want to divide them. So I want to take the limit then as n goes to infinity of n minus 1, n squared plus 1 over n plus 2, n to the fourth plus 2 quantity squared over 1 over n to the 6. So that's the limit then as n goes to infinity. Take this, flip this up. N minus 1, n squared plus 1 times n to the 6th over n plus 2, n to the fourth plus 2, quantity squared. Now, I want to find the limit as n goes to infinity of this. So I can multiply this out, use L'Hopital's rule. But again, I think it's easier, again, just to understand how you find limits as n approaches infinity. We're looking for the dominant power. The dominant power here is n to the 9th, right? There's n to the 9th on the bottom, n to the 9th on top. So what I'm going to end up with is the following. I'm going to end up with a limit that has an n to the 9th up top after I multiply the n times the n squared times n to the 6th, plus, I don't know, a whole bunch of other terms, which I don't really care about, over the denominator is also going to have n to the 9th, plus, again, a whole bunch of other terms that I don't really care about because they're not the dominant power. And then I'm going to divide everybody by n to the 9th. So when I divide n to the 9th by n to the 9th, I get 1. Plus, well, any of these other terms that are smaller than n to the 9th, when I divide them by n to the 9th, let's say n to the 8th or whatever, divided by n to the 9th, it gives me 1 over n. But as n goes to infinity, that goes to 0. So all these other terms are all going to wash out and go to 0. And then in the denominator, it's the same thing, right? I'm dividing by n to the 9th. I get 1 on the first term. And on the second term, everything else after that's going to give me a 0. So the result is 1. Well, this is a positive finite value. So then this series must converge by the limit comparison test. And that's the right answer. Okay? So again, it's easier to understand how this works. You don't want to multiply this out and then use L'Hopital's rule on it. And then you use L'Hopital's rule 9 times. That's not worth it. Okay, let's try another one. The sum from n equals 1 to infinity, 2 over 4 to the n minus 3 to the n. Again, I'm looking to compare this to another series. the series I want to compare it to is whatever dominates the numerator and denominator. Now, the 2 up there really doesn't matter, so I could really just put a 1 up there and hold its place with a 1. It doesn't make a difference. Okay? There are no variable powers up here. Underneath, there's a 4 to the n. Okay, so that's something to compare it to. So this is really 1/4 to the n. That's a convergent geometric series. R's between -1 and 1. And again, hopefully you're getting the idea now and starting to understand that, hey, all these other series tests keep popping up within these other tests. Yes, you have to know all the tests to make this whole thing work, make this whole chapter work. Okay? All right, so now I'm going to divide, or I'm going to take the limit then as n goes to infinity of 2 over 4 to the n minus 3 to the n over 1 over 4 to the n, which is really limit as n goes to infinity of 2 over 4 to the n minus 3 to the n times 4 to the n over 1. All right, I'm going to divide by the dominant power. Dominant power here is 4 to the n, right? That's the thing that ultimately controls what happens to this. The 3 to the n is not large enough. So I'm going to divide all these terms by 4 to the n. So that's 2 times 4 to the n over 4 to the n. 4 to the n over 4 to the n minus 3 to the n over 4 to the n. All right. As n goes to infinity, that's 2. That's 1. 3 to the n over 4 to the n as n goes to infinity. The 4 to the n is larger, so the larger term is in the denominator. That goes to 0. So the limit is 2. So now this is a positive finite value. That means since b sub n converges, then this thing converges by the limit comparison test. And that's the right answer. Okay? And that's all there is to it with the limit comparison test. And again, you can do the same thing. We did 2 convergent series with a divergent series as well. You just be comparing whatever series you want with a divergent series. Like, let's say the harmonic series, 1 over n. You compare this series with 1 over n, 1 over n diverges. And if you get a positive finite value after calculating the limit, then that series would have to diverge. Okay? That's how it works. All right? As always, thanks for clicking.